All right. Hello, everybody. Did anybody see my talk at CC?
Yes.
Yes. So I'm sorry. I'm gonna repeat all that. So, but you know, I'll wake you up when we get to the new stuff. So today we're gonna be talking about Canon, and Canon is our fault-proof system. And so I'm gonna walk you through how it works and some of the challenges we have here, and just generally the architecture of it. So, okay, this I might be able to skip. Does everybody feel confident, you know, how an optimistic rollup works? But, you know, it terms of scale because we want to preserve decentralization, so everybody should be able to validate the chain with a laptop. And optimistic rollups are secure because they are validators that download the batch data, the transactions from the chain, they re-execute them, and then they compare the output roots, so basically the state roots, commitment to the state of the output chain. They compare that to whatever the sequencer computed and posted on L1. This makes sense for everybody. It's like something. Don't hesitate. There's really no dumb question at any point. Just raise your hand. I'll try to check on you. Okay, so that was it. Optimistic rollups, very simple. The validators just check over the work of the sequencer. If they check the work and they find that they don't agree with the sequencer, which probably means that the sequencer either had a bug or tried to do something malicious, then they need to be able to challenge the output route that the sequencer posted. And they need to do this challenge on Ethereum layer 1. And the whole security premise of optimistic rollups is that as long as Ethereum layer 1 is secure, you will be able to prove correctly that the output route that the sequencer posted was incorrect. And so the whole point of this talk is to explain how you do that. How do you prove that the output route was incorrect? And so if Ethereum is secure, since all this happens on layer 1 contracts, the full proof will be secure. Yeah, this just reiterates all that. And this is just a graph that just say exactly what I said. We've got your verifier, downloads the batches from L1, also reads the output routes, he recomputes the output routes, compares them, if everything's the same, everything's peachy. If they're different, you start a fault proof.
Over slightly for the TV screen.
Yeah, I'm slightly in front of the TV screen, okay. Yeah, that's annoying because I need to. Okay, I'll just go back and push the buttons whenever that's needed. So how could you actually prove that the output route is incorrect on L1? These are all bad methods of doing it, but they're simple methods. So the simplest method you could do is just rerun, revalidate, and so rerun all the transaction, the L2 transaction on L1. And so to do that, for instance, you would have a EVM interpreter implemented as a smart contract on the EVM on L1. The problem is that running such an interpreter has huge overheads. I put 100x here. I actually don't know if that's a real number, but it's huge. You can't do it, right? Like, there's not enough gas in one L1 block to validate a full L2. So that's just not possible. So you might say, well, we don't need an interpreter, really, because L1 executes EVM opcode, and L2 transactions are also EVM. So why don't we just redeploy the L2 contracts and on L1 and just replay that there? The problem with this is that there are differences between the L1 environment and the L2 environment. So that's what I call contextual opcodes. So a good example of that is if you use the block number opcode, what you want from this is the L2 block number, not the L1 block number. So whenever in your L2 contract you have a block number opcode, if you're going to deploy this bytecode on L1, you need to replace the block number opcode by some call to a contract that keeps track of the current L2 block number. And the same thing, like you can't copy the whole L2 memory to L1. So you need to have a contract that manages the memory. And this gets complicated really fast, and it's still high overhead. So, you could say, well, could we do it for a single transaction? And this one's interesting because that's what Optimism tried to do, and it failed pretty badly. Because this is still not a very clean design, and you run into all kinds of gnarly issues. And one I thought was particularly interesting is because you're taking this L2 bytecode and putting it on a 1, you need to patch it to replace the contextual opcodes. The size of the patched contract becomes much bigger. But L1 imposes a maximum size constraints on the contracts. And so this means that in practice, contracts on L2 have to be much smaller to accommodate for this translation. And that's something users don't expect. And since the contract size limit on L1 is actually pretty small, it can be a real problem in practice. And that's just one of the issues, but it's illustrative of the kind of nasty things that happen when you do this. So the solution then is to use a challenge game. One of the challenge games is to figure out a single step of disagreement and only execute this step. So instead of executing, say, a whole transaction or a whole block, you will just execute a single step. And a step in this context could be one assembler instruction or one EVM instructions. There are different ways to do that, which we'll talk about. And the challenge game is played between a validator between a challenger and a defender, and the challenger is usually going to be a validator that verifies the chain, and the defender is usually going to be the sequencer itself that defends its own state root. So our system is called Canon. It was first invented by George Haas as a proof of concept that he handed to us, and I will explain what he gave to us exactly and what we need to do to make it production ready on L2. Developed by us, including me, and it's not the first system of its kind. So there's the CardEasy blockchain, does something similar. Arbitrum does something similar, of course. But it's the first system of its kind that supports full EVM equivalence. And as I said, it's also pretty slick. And what I mean by that is that it's a fairly minimal system that really goes to the core of what such a system is supposed to do, and doesn't include side concerns that are not relevant. So this is a design that could be retooled to do a bunch of other things. It's not limited necessarily to validating an L2 blockchain. You can prove basically any computation using this system. And we'll talk about that more in a minute. So, I said a step. We want to find a step that the validator and sequencer disagree on. What step is that? What's the process? So it's a step in an execution trace. And once being executed, so there's two ways to do it. You could execute EVM opcodes directly. And so your execution trace is a bunch of EVM opcode that have been executed when you run the transactions. One issue with this is that you still need to perform extra validation for the rest of the blocks. You want to verify that state roots are correct, you want to verify that all kinds of constraints the block have, difficulty or whatnot. Well, there's no difficulty on L2, but validate all the contract. And so you need to rewrite all that logic into smart contracts, and each time the hard fork on Ethereum, you need to rewrite all that also. The other way to do it, which is what we do, is that instead of executing EVM opcode, you execute assembly code that is the compiled version of your validation logic. And for us, the validation logic comes from Go Ethereum. So we just reuse the Go Ethereum logic wholesale to ensure that the blocks are correct. And that includes the EVM interpreter that is implemented in Go. And so we call this program over a miniget, and it's a subset of Go Ethereum because we delete a bunch of stuff, but we don't need to run RPC servers, for instance. And it's compiled to MIPS, and MIPS is an instruction architecture. And the only reason we chose MIPS is that it was extremely convenient because we can compile Go to MIPS easily. There's out-of-the-box support for that. And MIPS is a very simple instruction set. And so we have a very simple on-chain interpreter for MIPS that's just a few hundred lines of code. Is there any questions so far? Something someone would like to ask about? Okay. Yeah, I heard some. There you go.
Can you elaborate again why you prefer to go over the assembly opcodes of the get that runs the EVM like commands, or why that's better than going through the EVM opcodes? Why it's better to go one layer down?
So one big reason is that, like, executing the transactions is only part of the validation logic. You also need to update the Merkle try. You also need to, validate the header fields and things like that. And so that's all the logic you need to rewrite.
That's all baked into the assembly of code. Like, that's
Whereas,
translated into the assembly of code.
yeah.
Yeah, okay, makes sense.
Yeah. And that I would say the main reason. The main reason is that doing this is actually very easy. It's like, you will see it's very elegant. We don't need to write a bunch of custom smart contracts which you don't need to maintain because the Go Ethereum maintains Go Ethereum, right? So we just try to have a very minimal def on top of that, so we can just always keep up with whatever they're doing. And crucially, we also, this is also what we use in the rollup node. So this is the logic that's running, that we are running to the sequencer is running. And so it's that we are not maintaining two different implementations, which we then need to be convinced are equivalent. Here they're equivalent by construction. That's a good, a very good reason to do this. So then, okay, we want to figure out this step of disagreement and this execution trace. And the way we do this is playing this challenge game, which is a bisection process. You're a programmer, probably familiar with that. So we execute off-chain. We execute minigeth compiled to MIPS off-chain, and we execute it up to the midpoint of the execution. And we, at that stage, we take the memory and we hash it. We make a Merkle root. I'm going to say hash because it's easier to say. I was making the point that Merkle, I sometimes struggle to pronounce that. So we take a hash of the memory at the midpoint, and the validator and the sequencer, they both do this. And then they compare their hashes. If it's the same, it means they agree on the first half of the execution, so they will split what's left, and so you will take the hash of the memory at 75% and then compare and repeat that process. If they disagree, it means their disagreement is earlier, so they will take the midpoint of the first half of the execution, 25%, compare, etc. You continue narrowing the possible range of disagreement until you find a single step of disagreement. And so a property is that when you reach that, you agree on the memory before the step, so on the hash of the memory, meaning on the memory. And after the step, you disagree on memory, meaning you have a different interpretation of what that step does. Possibly, if someone is lying through their teeth, you disagree on the very first step. That's possible, but it could be later too. Once you find the step, you want to execute it on chain. So we have an on-chain MIPS interpreter. Very simple. Executing this instruction, like an instruction touches memory, so you need to know what the memory is. And the thing is, you have this Merkle root of the memory, so you can prove any byte of the memory against the Merkle root. And so basically what you do is that before executing this assembly instruction, you pre-supply the pre-images, you pre-supply a Merkle proof that say, well, the byte at address 100 in memory is this byte. And so when you execute the instruction, you can access it, and it's probably correct because both parties agree on the hash before the instruction. So that's for accessing the memory. There is a special case where you want to access data that's from the L1 chain, and that is the batches themselves, right? The whole point of the process is that there is the canonical data, the batches, the transactions are posted on L1, and you want to take those, convert them to the L2 chain, and execute that. And so for that, you need to access this L1 data. And for this, we use a component called the pre-image oracle, which is the real mind blower of this whole design. We will explain it in depth in a hot second. Okay, and this is just a graphic that explains the bisection game. So, take a memory hash at 50%. So these are the execution trays of the defender and challenger. Every square represents an assembly instruction. Yeah, you have a question.
Is this done on-chain or off-chain?
So each agent, so the challenger and defender, they execute miniget compile to MIPS off-chain.
Yeah.
Then they off-chain, they take a snapshot of the memory, and then they submit it on-chain, and that's where the comparison happens. So on-chain will track basically the possible range of disagreement. So at the start, the challenger will say, well, I think the execution is 10,000 steps. So the range is 0 to 10,000. Then, so both of them will execute to 5,000 steps. And if they agree, then the range will become 5,000, 10,000, etc. Yeah?
You just said that they execute off-chain miniget comparison MIPS.
Yeah, exactly.
So they don't use like a native version for that. I thought that they will always execute like the native parameter.
No, you execute the MIPS version, and the reason that you do that is that you want to take a snapshot of the MIPS memory so that you can execute the step on
So
chain.
you have like a MIPS VM thing. I mean, there's probably some official.
Yeah. We have I think I'll briefly touch on that. So we basically use QEMU, the emulator. We have a library that just runs QEMU and executes the MIPS. Eventually, if we scale, it might be that we need to get MIPS hardware to make that fast enough. But before that, that's fine. So yeah, so we do this comparison. Let's assume it's the same. It takes 75%. Again, computational memory is different. You cut in half each time until you find a significant figure. Just a graphical illustration. All right, preimage oracle. So the preimage. Oh, actually.
In this context, the execution trace is the one between the roots of a block, the transaction, block.
Yeah, that's correct. So you would, so the way miniget works currently is that you pass it a block number, and it will execute that block transition.
Okay.
So it will use like the on-chain root for the previous block or the previous. Actually, it won't really be a block because we don't checkpoint every single L2 block.
Right.
So it's actually will execute a bunch of blocks between two checkpoints. Yeah.
I was gonna say, you could do the back and forth bit off-chain, like if nothing's stopping you, just more overhead, you kind of like have to communicate and have some bonding contract. But it technically isn't impossible to do that for off-chain.
Yeah.
So the challenge back and forth is on-chain. Like he puts the snapshot of the memory, including like all those individual steps where it's merkalized.
So you pose the.
Like when you have that big chain of memory blocks, is that what's posted on chain, or that's probably merkalized, right?
Okay, let's see the back. So what you're posting is the Merkle root for the memory.
So the Merkle root of those sort of blocks, right?
But those are not blocks, yeah. Sorry.
They're the memory, but they represent just blocks.
They're not even the memory, actually.
Okay.
They're each one is an instruction actually. So it's a step. It's like, okay, first you execute add, then you execute null, then you push whatever. And so, you're running all these instructions, then you stop. You say, oh, this is step 5,000, I'm stopping. Look at the memory right now, merkleize it, submit it on chain, and then it's just 32 bytes. And so each of those is one transaction, and then so they will have to do basically log of the size of the trace transaction, each of them. Yeah. All right. So preimage oracle is a component whose interface is very simple. It's a function that, given a hash, returns preimage, which of course it's something impossible to compute, so it will need to know about these preimages in advance, right? And so in the case where you have an on-chain preimage oracle, it means the preimages was pre-supplied to the contract, for instance. Now, this is very useful in a few cases, and the cases that we're really interested in are those. So if you have a block hash, it means you can get the block header. It's a preimage of the block hash. And this means you can use those hashes to walk the chain backwards because each header also has a hash of the previous block. right? So you get a hash, expand the header, read the previous hash, expand that, and so you can walk backwards through the whole chain. Each block also has Merkle roots for a bunch of things, so for transactions and for state, most notably. And the thing is that a Merkle try node is a hash of its children. So if you get the preimage of a node, it means you can get its children, so you can use the preimage oracle to traverse the tree downwards. And so when you put these things together, it means that using the preimage oracle, it's a fully general interface that lets you access any L1 data, right? You can walk the chain backwards to any point in the past, and then from there, you can go down the Merkle trees and find any kind of data you want. So you have a small, well, not so small, an illustration of this here. So say we're trying to read the transaction batches, and these are, in this case, in block 41. So we start with the block hash opcode, gives us a previous block hash. This is block 42. What we want is in block 41, so we read the previous hash, get the preimage. So the green arrows show you the path we're taking and invocations of the preimage oracle. So preimage. In there, we read the transaction Merkle root, and we expand. We get the preimage of every node, which is its children, and we traverse in that way until we arrive to the leaves, which contain the transaction batch in this case. In reality, when you're scanning for transaction batches, you'll need to expand everything and read all of them.
But sir,
Yes.
can you repeat once again? How can you do this? How can you know the previous block hash? I mean, you have a block hash of the previous block, and then you need to prove what's the block hash of yet previous block, right? Like you read the part. Do you need to dump all the information from the block to do that? Like, how would you go from the hash of a block to prove that there's certain value there?
Which one you mean, like from a hash to say from a block hash to a block header, for instance?
Yes.
So you need to get that info from somewhere. And we will see how you get that, because I can basically give you a spoiler, which is that we run minigeth. We also compile it to x64 at some point, and we run that, and then we just talk to L1 node, and we use the RPC to get the preimages. So there are some RPC calls you can use to get preimages. And so for the block hash, it's very simple, because you just use this RPC call called ETH get blocked by hash, and that does exactly that. You pass it the block hash, it gives you block header, so it's basically a preimage in the case of a block hash. It's a little bit more tricky for Merkle root tree, because there's no direct thing where you give it a hash of a Merkle root node and it gives you its preimage. So you have to be a bit more crafty, but I will talk about that.
And this is part of the system, like execution. Like you wouldn't execute it, you would do the challenge game on that, correct?
Okay, it depends what you define as the fault-proof system, I guess. So the execution of minigeth that you're proving assumes it has access to the preimage oracle. So it assumes that the preimages are known and can be supplied. In practice, they are, because you can get them from L1, right? So any agent that has access to L1 can get the preimages, and so can prove the execution based on this component. Yes.
Give an example where you get information about L1, about batches during the whole group.
Yeah. So basically, when the start of the validator, the start of minigeth in its final version, it knows it needs to validate. Let's say it needs to validate a single L2 block. We know from the way the chain derivation works that all this information on this L2 block is going to be contained on a certain range of L1 block. So the first thing you're going to do is walk all these L1 blocks. Maybe you just walk back to the first one of those. And for each of those, you are going to look at the transaction data and find all the transactions that are being sent to the batch emitter contract on L1. Basically, you're gonna walk all the transactions and find those that are of interest to you. And so this mechanism uses a pre-image oracle. But off-chain, right? On-chain, we only ever execute one step of that, which is trivial. Want to say something? Yeah?
Cool, that's a question. What stops me from submitting my own, like, alternate on-chain as a pre-image kind of set?
Submitting your own element. I think I see what you mean. Like, you can submit any, so there's a contract that receives pre-images. You can submit any pre-image and we'll store it. The thing is that there's an ultimate source of truth, which is bytecode. That this is executing on L1, and so you basically get the previous hash on L1, and that's your ultimate source of truth. And anything needs to derive from that. And so if you give me a pre-image that's in an hypothetical Merkle try that isn't actually on L1, it will be there, but it will be useless because you can actually never get. You can actually never prove that it relates back to the block hash.
But then you're talking about potentially doing like hundreds of thousands of blocks in the past, right?
Potentially, I mean, I don't know about the numbers, but yeah, potentially you can do like quite a bit. It's like bounded by, so it depends the number of block transition that we need to execute. And then it depends on the size of the window, so where, for a given L2 blocks, which range of L1 block need to be read. Yeah. Alright. So, how does this component integrate with Minigath? Basically, Minigath replaces the state database from Go Ethereum with the pre-image oracle. Because when you think about it, well, the state, as we've seen before, is just a big Merkle root. So you can re-implement the DB using the pre-image oracle. It's the same idea of traversing the tree. We actually have three implementations of the pre-image oracle. We have the on-chain one, in which you just supply the pre-images and then just is able to give you those pre-images that you pre-supplied. We have the off-chain MIPS implementations, which, as Chris asked, is the whole purpose of that is to get the memory hashes. And that uses the hashes that have been prefetched by the off-chain x64 version of Minigath, which uses using RPC methods to get the pre-images. And so those code we use in particular is get block by hash. Maybe explain just get block hash, get the pre-image. 4 Merkle root nodes use ETH get proof, and that sends you a Merkle proof of a storage slot, basically. And there's another one that I forgot on this time, which is you can get the code of a certain contract also, and you also need that because I don't remember which you do. Okay, so this was the summary of my original ACC talk, so interesting stuff coming up. So Optimism rollups are secure as long as there's one honest validator, which checks over the working sequencer. If the validator finds the sequencer does not agree with them, he starts a fault proof, and they will work together through this bisection to find a single step of disagreement. And then that single step is executed on-chain. The MIPS memory can be proved against a Merkle root of the memory hash, and the batches can be read from L1 using pre-image oracle. And okay, so where are we on all this today? So George sent us a prototype which lets you challenge L1 blocks on L1. This is not super useful because by definition L1 blocks is valid, but it proves the concept. What's almost done is porting this to L2, so you can challenge L2 blocks in L2, And what this proves basically is that the extra logic that we added to Go Ethereum, so we added a new transaction type for deposits, for instance, that this doesn't break the logic. What comes next is challenging L2 blocks on L1. And so that requires adding the part that reads the transaction batches and does chain derivation to miniget. That's not in there currently. It's not going to be so much work, at least we don't expect it to be too much work, because we already have this code. This code is in the rollup node, it's written in Go. So what we can do is import the Go module, implement this directly into miniget, write some wrapper logic around it, and then we're good to go. So we don't have to maintain two separate implementations. And the only reason that actually it's not like that already in the rollup node is that we want to have this separation between the rollup node and the execution engine. That's very key. Now's a good time for like some general questions before I get to like more hard stats. Yes.
So what's the gas cost of Optimism?
That is a good question. So it's every like transaction where we submit a memory root is fairly cheap, but we'll need to do like, well, log of the trace, so you know, maybe $30. But if you have 4 billion steps in your execution trace, it'll be 32 steps, for instance. So you know, that's 30 transactions, and then you need to do the final transaction that executes the single step. That's also fairly cheap because you know you read a few storage slots, do a very, very simple computation, and then you know, yeah, build a macro at the end. So it shouldn't be too expensive, and the key thing is that there's like a bond for sequencer at stake that should be a significant amount of money. So you're talking maybe hundreds of dollars to run this in a bad case, versus maybe, you know, hundreds of thousands or a million or whatever. I don't really know about the value of it, but it will be worth it, basically. So I think we've touched on this already a little bit. This is what's in miniget, how does it work? So you start with Go Ethereum here at the bottom. And then we have a small diff on top of that, which is currently in a repository called Optimistic Reference Get. Terrible name that Carl came up with. But we've been calling it the execution engine. L2Get is also a cute name for it. And this just adds the minimum logic on top of get to support, for instance, deposits, and then configure a few things like the mempool was private currently, so that's configured there. And miniget is on top of that, so it's really like this is the upstream of miniget, and then Go Ethereum is the upstream of L2Get. And in miniget, we delete a ton of things from there because we don't need JSON RPC, we don't need a bunch of R-generative consensus logic, we don't need to do proof of work mining, things like that. So all that we can just delete the code downright. We re-implement the database via the pre-image oracle PO here, and then we implement this thing with the L1 fetcher via the pre-image oracle. Now I'm gonna explain what the L1 fetcher is. So basically, what the components or L2Get of miniget are is L2Get, the thing that validates L2 block for our custom version. Then in front of that, we need to stick these Go modules I talked about to do the rollup derivation. So read the batches and actually derive the L2 block. And then you can feed that block directly to the logic from L2Get. Both of these steps use the pre-image oracle. For L2Get, this is to access the state of the L2 blockchain via the pre-image oracle. For the rollup node, it's via the L1 fetcher. And what the L1 fetcher is a very simple interface that lets you access any data on L1. So give me a block by its hash. Give me a, let me access the transactions on this block, something like that. And so we just need to implement this interface using a pre-image oracle, and that's all this needs. And so the reason this is an interface is because this code is going to live both in the rollup node, where it will use an actual L1 to answer these queries about L1, and in minigeth, where it will not use L1, where it will use the pre-image oracle to answer these queries. That's sort of how minigeth is working, and how it's implemented and what its different components are. Okay, so this is my spaghetti graph. It got a little bit out of hand, but we'll untangle it. So you can start here with L1, and you have your normal rollup nodes, not minigeth, your normal thing that already exists. That's gonna read L1 block and just progress the L2 chain normally. If you're a verifier, you also get the output truth that's not on there. And you will check what the sequencer did. And if you disagree, you trigger a fault proof. And that's where minigeth enters the pictures. Yes.
The knowledge that is progressing at the state is using different execution engine that is used for outputs, because that's what you do. Minigeth is what you use for fraud.
Yeah, exactly. If there's no fault proof, you don't run minigeth. Yeah.
But if there is a bug in eventually if there is a difference in implementation of these two engines, then you may get wrong state, wrong L2 state that you won't be able to prove with your minigeth implementation because they will agree.
Yeah, there is a risk there. That say there is a bug in the rollup node that's not present in minigeth, for instance, and so you just say, yeah, the sequencer, great job, and actually there's a bug. And if you had run minigeth, they have found the bug. So there's two things I can say about this. One is that we've designed this so that minigeth and the rollup node are as close as possible because they use the same Go code. So that should mitigate the divergence between both as much as possible. The other thing is that eventually we want there to be multiple implementations of the rollup node and multiple implementation of the fault proof, so that we can, catch bugs that would be in all those together. But that's like a longer term vision, but yeah, you bring up a perfectly valid point there. Does that answer your question?
Would it be also possible to just simulate like the execution, using the minigeth, simulate in like a fork mode of one, and just pretend that we're doing proofs to see if there's a bug. Basically we could find if minigeth disagrees with rollup, but of course you need a beefy machine.
Yeah.
So execute so many blocks, right?
Yeah, so you would just run minigeth on everything basically in parallel.
And which engine is used by validators? Is it
Is there always a rollup?
Yeah.
rollup?
So here's the rollup node, and well, if you want to be strict, like the rollup node also talks to the execution engine. It's just like the whole thing, right? Like the whole. There's also one get in there. Right? Yes.
I think in theory, we should get to the point where you have a really highly parallelized, really efficient minigeth that you can run with kind of follow the chain close to shit. We think that's possible. It's just that's not the main goal.
Yeah. So there's no latency requirement on that, and so you can just have 100 machines that in parallel play the last 100 checkpoints. So it's easily parallelizable for sure. But yeah, indeed, there's a lot of overhead in minigeth, especially currently where we emulate it on QEMU. That's a lot of overheads. Using the pre-image oracle might add some overhead. I'm not too sure about that. So yeah, good questions or good discussion. So say we trigger a fault proof.
And so So
Yeah.
some rough assumption for image oracle is that it doesn't lie about L1 state that is providing.
Yeah, so the preimage oracle on-chain cannot lie because you send the preimage and then it hashes it and then it stores a mapping from the hash to the preimage. So you cannot supply a bad binding because it recomputes the hash. See?
You check with that.
So why is it called oracle then? There is no, what's the solution?
Oracle doesn't mean transaction, it's just that it's a little bit magical because normally you can't inverse a hash, right? So it's sort of this black box that magically is going to give you the preimage, but in reality it means you need this info from somewhere else in practice, yeah. But it is secure as a component. Oops, I went a little bit too far. So yeah, we're running a fault proof. Then we're going to use miniget, and the first thing we're going to do is to run it, to compile it in x64 or whatever your architecture is, that is fast. And this is what we call prefetch mode, because we use JSON RPC call to L1 to get the preimages. You have a question?
I just want to make it, you mentioned like in passing you for like adding a preimage oracle has some sort of overhead, like you might add some overhead for running that process. Like one thing that's worth noting is that beam sync, which is this syncing method for get, is basically that same technique. You know, like you're constantly loading things. So like, there's already work being done to create a syncing method that is basically the equivalent thing that we're talking about here. It's not like this is in that language idea, this is already been worked on.
Yeah, very true. So, yeah, prefetch mode, you get all the preimages from L1 directly. So you hold on to those. Then you also compile miniget to MIPS. You get a binary. Then there are some technical details because when you compile to MIPS from the Go compiler, it sort of assumes you have an operating system. You know, if you don't have that, so you need to add a small loader routine in front of it. So if you're familiar with compilers, what Go produces is an ELF module. And so you sort of need to tell it, oh, you need to jump here to start executing code here and stuff like that. And also it removed the garbage collector from Go because that's concurrent. And we don't support concurrency in this process, we just want a single linear execution trace. And this is done, like if you're looking at the code, it's done in a directory called Nipigo. This is another terrible name we wrote. Things we need to rename, but I don't know why it's called Nipigo. And so you get this patch MIPS binary, then you feed it to another program called MIPS EVM, and that's just another terrible name, but it's a MIPS runner. You take this MIPS binary, and it just runs QEMU and executes it. And it's also able to stop at a certain step to take a snapshot and hash of the memory. So it does all that. So when you run MIPS EVM, basically the whole goal of that is to get the memory hashes, the memory Merkle roots. And a few of those is that the initial one. So that's the one when you haven't started. So you haven't started the computation. So the memory at this stage mostly only contains the code itself. And that's kind of important because you could hash that on-chain, and that's basically the source of truth for the behavior of your rollup. It's a commitment to the code that validates the logic of the rollup. And if you look at the code, George called this the golden hash. Then you have the checkpoints for the challenge game, 50%, 35%. And then you have the final state that basically tells you which contains a certain location the output root that is supposed to be computed. So you can get that from our root. So, and to run this, you need the preimages you got from prefetch mode, right? That's pretty important. So, we run MIPS EVM to get all these Merkle roots via the preimages we have. And then we feed all those to another component called the challenger agent, or if you're a sequencer, the defender agent. And this component just plays the challenge game. So it just monitors the chain. It says, hey, I want to do a challenge. Here's my midpoint memory hash, and then it waits for the defender to respond, and once it sees the defender has responded, it goes like, okay, you think we agree, so now let me give you the 75% hash, etc. So there's a feedback loop here where the challenger agent is basically driving this whole process. Whenever it needs a new memory hash, it will call MIPS EVM to get that. And so it plays the game with that one.
So in reality, how long does it take to play this game? Because you interact with L1, you progress the game by sending transactions. So both parties need to send transaction to L1 to progress it to the next step, right?
So
to the next section.
Yeah. So the absolute best case is going to be some fixed number of transactions, 2 or 3, and then the logarithm of the size of the execution trace, say 30, times 2, because they each need to ping and pong. You know, like they each need to send for every step in the bisection game. They each need to step 1. So in the best case, it's going to be like about 70 blocks, right? And then, but then they can also.
What if one of the parties tries to delay the process?
Yeah, exactly. That's so if the challenger delays the process, it will lose by default. So basically, how it works is that there is a challenge period, and it's implemented as a chess clock. So basically, you got, say, 7 days to do all your transactions. And so if you take a long time to submit one answer, you get less time to submit all the other ones. The idea being that this time they will give you in total is enough for you to do all the steps comfortably, right? And so the maximum time will be twice that. So I have no specific numbers for time, but it could be like half a week. So each of them gets 3.5 days to do all their transactions. And so the max time that this could take is like 7 days, which will be, you know, twice this amount. Well, it's actually the same. So if a party does not answer, they lose by default, basically. Yeah. Another question? No?
Is there any pretty much Oracle with the smart contract, right? It's each on chain and stores on-chain information.
Yeah.
Right? Is there any thought about the cost of it? Like as we grow nearly, the more hashes we add. As the system works, we need to add more and more hashes to the smart contract.
Yeah, that's a problem for Ethereum devs. Because we add that into it, but first of all, we don't expect there to be a lot of challenges.
Who will solder the cost? Who will solder the
The person that posed the preimage shoulders the cost. So when but it's really cheap, right? Like, so you do the whole bisection game, and then you need to execute the final step. And any of the two parties need to execute the final step.
The challenger. Because
I
assume the defender is malicious and
the challenger is, I think, on the hook for that one. Like, but the challenger can also, it's actually anybody, when you reach that step, anybody in the world can challenge it, because you have all the information necessary.
I'm coming from an incentive, so the challenger is incentivized to because he wants to punish and stop the system.
But it's not expensive, right? Because you just, so one single MIPS instruction will touch at most a few locations in memory, meaning you will need to submit 2 marker proofs and maybe 1 or 2 preimage, thing. And so the cost of that is the cost of 2 expensive transactions, like maybe in the worst case like $50 each. And so compared to what you win, it's trivial. Yeah.
And also the fact that the system like this exists and works will prevent from from happening basically. And the state growth of this contract is not going to grow too much.
Yeah, because each successful fold proof and even each unsuccessful, because the challenger also needs to put stake. Each fold proof that goes through is going to cost hundreds of thousands of dollars. So probably people want to frivolously do those.
Nice.
How are we doing on time? We're almost done. I can talk you, so only thing I have left here are like highlighting 2 challenges that came up in the work we've done on so far, which are interesting. And this one will be easy to explain. So, you know, single-step execution requires you to post the pre-images on chain. Most pre-images are small, so that's not a problem because you always post the whole pre-image. You know, a block header is very small. A Merkle node is very small. There is one exception: is the receipt hash for a single transaction. So you get a receipt root in the header that encodes all the receipts for all the transaction, but the receipt for a single transaction is the hash of all the data. It's not Merkleized. And so if you're a malicious actor, what you could do is just take up the whole gas of an Elven block and just use all that gas to do a ton of data. And if you do that, there is a big asymmetry because 1 byte of log data costs 8 gas, but then this needs to be posted on chain, right? Like if you do a fault proof and you need to access this pre-image, you need to post the whole thing on chain, but the price for 1 byte on chain of cold data is 68 gas. So that's like more than 8 times the amount. And so this is a big DOS vector for fault proof. So what we're thinking of doing there is to use a simple zero-knowledge proof, because the MIPS instruction will not need to read the whole pre-image. It just needs to access 1 byte or 1 word of that. And so if you have a zero-knowledge proof that is able to prove that a single word in the pre-image at a certain address is this, that's all you need. And so we need to look into this, but I think this should be fairly easy to do with off-the-shelf tools. Like we can do a circuit, and that will be very simple. I'm not sure I should launch into this one. It's a little bit difficult. But basically, let me just give you the pitch, and then if you're interested, you can ask me questions about it later. So I told you that it could be slightly tricky when you run miniget in fetch mode to get the pre-images of the nodes. The way we do it is that we get a Merkle proof for those, but there is a very tricky scenario there. And the tricky scenario is basically when you remove a node from the Merkle root. So you know, this happens when you execute an instruction, it clears a storage slot. Then you need to remove a node from the Merkle tree, and you need to, you know, propagate this change in the Merkle trie. So the root will be changed. And there is one case where that's super tricky, and that's when you have this thing called a full node is a Merkle root node that has more than 1 children. And you also have another thing called a short node, which only has 1 children. And basically, it lets you compress a path of multiple nodes going down. So let's say that your key is ABC. You need to have a node for A, a node for B, a node for C. You just have 1 ABC and then the child. And if you have a full node in very particular terms that has 2 nodes, you delete 1. Then you have a case where you could have 2 scenarios after that. And finding out which one you need to do is tricky. I'm not going to enter the detail. The solution to that is interesting because it's actually looking at the Merkle trie after the block transition. So, you know, when you execute things, you assume that you start from the starting trie and you just make changes to it. But because you're validating, you already know what the sequencer claims is the final tree. And you can actually use that to solve this issue. That's all I say about that. So if you're interested in that, ask me. It's not a super important problem because we could just have done a JSON RPC call on Geth that just gives us pre-image directly. So it's not a fundamental issue. It was just, you know, one that we spent some time figuring out and solving. So I figured that I like that as the kind of things we run into. That's it for my talk. and if there are any more questions. Okay, we're good.